When you're big but not fast, going underground where predators can't easily follow you is a smart strategy. Either way, it shows these animals were way more behaviorally complex than we might expect from something called a giant sloth. Here's another fascinating discovery about ground sloths. In Ecuador, at a site called Tank Loma, paleontologists found the remains of at least 22 aromatherium sloths of various ages, all in the same location. They likely died during a drought, getting trapped in a shrinking watering hole. But the cool part is what this tells us about their behavior. They were congregating at watering holes, which means they were social animals living in groups. And they were probably wallowing in the water to escape heat and insects, similar to how hippos and rhinos behave today. It still amazes me that even during ice ages, not every place was frozen. Tropical and subtropical regions still experienced warm seasons. The climate was cooler and drier, yes, but equatorial areas weren't buried under ice. So, even then, animals had to cope with heat. It's fascinating to think that ground sloths in South America employed strategies similar to those used by large African mammals today. The Ice Age wasn't a planet-wide deep freeze. Speaking of amazing finds, let's go back to mammoths. The specimens preserved in Siberian permafrost have revealed so much. Some even have their last meals preserved in their stomachs. I remember being stunned when I first read about scientists examining this material and finding grasses, sedges, herbs, flowers, mosses. It's like a snapshot of the mammoth steppe ecosystem and the available plants. But it gets even better. We've extracted DNA from these frozen mammoths, sequenced entire genomes. The genetic analysis revealed some incredible adaptations. Mammoths possessed variants of hemoglobin, the protein that carries oxygen in blood, that functioned better in cold temperatures. Normal hemoglobin doesn't release oxygen efficiently when it's cold. Mammoth hemoglobin had mutations that compensated, allowing their blood to deliver oxygen effectively, even when their body tissues were cold. That's hardcore molecular adaptation. We've also found that mammoths had genes for smaller ears, sparse sweat glands, and improved fat storage, all coded in their DNA. Evolution didn't just change their external appearance, it rewired their physiology at the genetic level. There's something almost poignant about the last mammoths, those that lived on Wrangel Island in the Arctic Ocean. This island was cut off from the mainland as sea levels rose after the ice sheets melted. A population of around 500 to 1,000 mammoths survived in isolation there until about 4,000 years ago. Just imagine, 4,000 years ago is after the pyramids of Giza were built. That's during the Bronze Age. Mammoths and ancient civilizations overlapped in time. The last of these giants walked around on a remote Arctic island while humans in Egypt were building monuments and developing writing. Then they went extinct, probably due to a combination of inbreeding, habitat degradation on their small island, and possibly climate change or human arrival. It was the end of an evolutionary line that had lasted for millions of years. Woolly rhinoceroses are another species we know a lot about from frozen specimens. Like mammoths, they had thick, woolly coats and were built for the cold. But their behavior was probably different, based on their tooth wear and the isotopes in their bones. Scientists believe woolly rhinos were more selective feeders than mammoths. While mammoths were bulk grazers, Eating whatever vegetation was available, woolly rhinos seemed pickier, probably using their horns to dig through snow to find specific plants they preferred. And then there's the giant deer, Megalochirus, with antlers that were absolutely insane. The largest specimens had antlers spanning over 312 meters from tip to tip, wider than a car. These antlers could weigh up to 40 kilograms. Carrying that much weight on your head required serious neck and shoulder muscles. Scientists think these massive antlers were primarily for display and competition between males, similar to how modern deer use their antlers. During mating season, males would show off their antlers to females and use them in battles with rival males. The bigger your antlers, the more impressive you looked. But those antlers came at a cost. Growing them required huge amounts of calcium and energy, and carrying them around was energetically expensive. Only the healthiest, best-fed males could support truly enormous antlers. Cave bears are interesting because, despite their name and size, they were mostly herbivorous. Isotope analysis of their bones shows they ate primarily plants. They were built like grizzly bears but acted more like giant pandas. They hibernated in caves during winter, which is where we find most of their fossils. Some caves in Europe have thousands of cave bear bones, representing hundreds or thousands of individuals that hibernated there over millennia. Cave bears went extinct earlier than many other megafauna, around 27,000 to 24,000 years ago, well before the end of the last glacial period. The reasons aren't entirely clear, but it might have been related to competition with humans for cave space, climate changes affecting their food supply, or a combination of factors. Glyptodons still blow my mind the more I learn about them. Recent studies of their skeletal structure and muscle attachment points suggest they were capable of some surprising behaviors. They might have been able to rear up, as we mentioned, but they also show adaptations for powerful digging, similar to what we see in modern armadillos, but scaled up massively. So, these armored giants might have dug burrows like their ground sloth contemporaries. I try to imagine tunnels big enough for a Volkswagen Beetle to drive through, created by armored animals with spiky tails. The Ice Age was truly wild, and the predators of the Ice Age were just as specialized as the herbivores. Saber-toothed cats didn't just have those impressive fangs for show. Biomechanical studies of their skulls show they had relatively weak bite forces compared to modern big cats, but their neck muscles were incredibly powerful. Their hunting strategy was probably to use their strong forelimbs to wrestle prey down, then use their neck muscles to drive those saber teeth deep into the prey's throat or belly with precision. It wasn't about crushing force. It was about precision. Dire wolves, those massive predators of the Ice Age, have been studied extensively. The La Brea tar pits have given us thousands of their fossils, a haunting testament to their lives and deaths. Imagine them, trapped in sticky asphalt, struggling to scavenge a desperate act that became their doom. What I find particularly striking about these fossils is the story they tell of hardship and resilience. Many dire wolf specimens show broken teeth, healed fractures, and signs of arthritis, especially in older individuals. This suggests a social structure, a pack dynamic where injured or elderly members were cared for. A wolf with broken teeth simply can't hunt alone. It couldn't survive without the pack-sharing food. The fossil record really does point to complex social structures, much like modern wolves. Then there are the giant short-faced bears, still shrouded in some mystery. Were they primarily predators or scavengers? The evidence is mixed, which only deepens the intrigue for me. Their long legs suggest they could cover vast distances efficiently, perfect for scavenging, but their powerful jaws and teeth, those were definitely capable of killing prey. Perhaps they were opportunistic, hunting when they could and scavenging when necessary. And their sheer size, possibly the largest mammalian land predator ever. That alone suggests they could easily intimidate smaller predators, stealing their kills. I imagine a pack of dire wolves bringing down a bison, only to have one of these giants show up, chasing them off to claim the carcass. One of the coolest things about understanding Ice Age ecosystems is this unusual source of evidence, ancient DNA in sediments. Even without bones or visible fossils, DNA from animals can be preserved in frozen soil. It's remarkable. Scientists have developed techniques to extract and identify this environmental DNA, and it's revealed which species were present in different places at different times. It's filled in gaps in the fossil record, showing us that Ice Age ecosystems were even more diverse than we realized. For example, we now know that horses were present in areas where we don't have horse fossils because we found horse DNA in the soil. And it's not just animals. We've identified plants that grew in certain regions by finding their pollen and DNA. We can even tell what the climate was like by looking at which species of plants and insects were present. It's like reading an ancient ecological record written in genetic code. Humans, of course, were observing and interacting with all of this megafauna. They left records of what they saw. Cave art from sites like Lascaux in France and Chauvet Cave show remarkably accurate depictions of Ice Age animals. The artist painted mammoths, woolly rhinos, bison, horses, cave lions, and more. And these paintings aren't crude stick figures. They're sophisticated artworks, showing animals in motion, even using the natural contours of the cave walls to create three-dimensional effects. The artists clearly spent a lot of time observing these animals to capture them so accurately. Some cave paintings even show details like fur patterns, seasonal coat changes, and behavioral poses. There's a famous painting of a woolly rhino that clearly shows its thick fur and the way it held its head. There are paintings of mammoths that show their characteristic domed heads and long tusks. These artworks are our direct visual record of what Ice Age megafauna looked like, created by people who saw them alive. Humans also left behind butchered animal bones, showing clear-cut marks from stone tools, mammoth bones with spear points embedded in them, campsites with hearths surrounded by the remains of horses, bison, and reindeer. The archaeological record proves that humans hunted megafauna and relied on them for food, materials for tools and clothing, and fat for fuel. Mammoth ivory was carved into art objects and tools. Hides were used for clothing and shelter. Bones were used to build dwelling structures in areas with scarce wood. Every part of these animals was utilized. But humans weren't just passive observers or simple hunters. There's evidence that humans might have used fire to manage landscapes, creating and maintaining the open grasslands that megafauna depended on. By burning vegetation regularly, humans could prevent forests from encroaching on grasslands, keeping habitats open for the large herbivores they hunted. This kind of ecosystem engineering might have actually helped support megafauna populations in some regions. So, the relationship between humans and megafauna was complex, not just predator and prey. The 100,000-year cycle had created this entire world. The cold phase of the cycle produced these unique ecosystems and drove the evolution of specialized megafauna adapted to frozen conditions. For hundreds of thousands of years, the pattern repeated. Ice sheets advanced. Megafauna thrived. Ice sheets retreated. Forests expanded. Ice sheets advanced again. Life adapted to this rhythm. But then, about 19,000 years ago, the cycle began shifting toward warming again. And this time, something was different. This time, humans had spread across most of the world, developed sophisticated hunting technologies, and existed in larger numbers than ever before. This time, when the climate started changing and the ice began to melt, the megafauna wouldn't just adapt and wait for the cycle to swing back to cold like they had for hundreds of thousands of years. This time, most of them were going to disappear forever. And we're still debating exactly why. Around 19,000 years ago, the 100,000-year cycle reached a turning point. The orbital configuration shifted into a pattern that favored warming. Northern Hemisphere summers started getting stronger, receiving more solar radiation. And when that happens, winter snow starts melting more completely each summer. Ice sheets stop growing and begin their long retreat. The transition from glacial to interglacial conditions was underway. The thing about deglaciation is that it's messy. It doesn't happen smoothly. It comes in fits and starts, with sudden collapses and temporary reversals. There are periods of such rapid change that they would have been noticeable within a single human lifetime. And this very messiness is what makes understanding the extinction of the great beasts so complicated. The first major pulse of melting kicked off around 19,000 years ago, and it continued for several millennia. As the ice sheets melted, sea levels began to rise, pouring water back into the oceans. During one period, known as Meltwater Pulse 1A, around 14 to 600 years ago, sea levels rose by roughly 20 meters in less than 500 years. Now, 20 meters might not sound like much, but think about what that means. It's enough to flood vast coastal areas, to submerge land bridges, and completely transform coastlines. All that water had to come from somewhere, of course, and it came from the collapsing edges of the great ice sheets. The Laurentide ice sheet, that massive dome of ice that covered Canada, began breaking apart. The Fennoscandian ice sheet in Europe did the same. As they melted, they left behind a landscape that had been compressed under kilometers of ice for thousands of years. The land was scraped clean, covered in glacial till, dotted with lakes formed in depressions carved by the ice. It must have been a raw, bare landscape at first, slowly being colonized by plants as the climate warmed. But the warming wasn't steady. There were dramatic interruptions. The most famous of these was the Younger Dryas event, and it's quite a wild ride. By around 140700 years ago, the world had been warming for thousands of years. Ice sheets were in retreat. Things seemed to be heading toward interglacial conditions. Then suddenly, boom, temperatures crashed. In Greenland, temperatures dropped by about 15 degrees Celsius in just a few decades, maybe even faster. Some evidence suggests it could have happened in as little as 10 to 20 years. The North Atlantic region was plunged back into near glacial conditions that lasted over 1,000 years. What could have caused this dramatic reversal? The leading theory involves a catastrophic flood. As the Laurentide ice sheet melted, water pooled up behind it, forming enormous glacial lakes. The largest was Glacial Lake Agassiz, which was bigger than all of the modern Great Lakes combined. This lake was dammed in by the ice sheet itself, and when that ice dam failed, geological evidence suggests it did multiple times. Absolutely stupendous amounts of fresh water flooded into the ocean in a geologically instant time frame. We're talking about enough water to raise global sea levels by several meters, all released in months to years. This massive freshwater dump disrupted ocean circulation in the North Atlantic. There's this ocean circulation pattern called the Atlantic Meridional Overturning Circulation, or AMOC. It's basically a conveyor belt where warm surface water flows north, cools down near Greenland, becomes dense and sinks, then flows south at depth. This circulation transports enormous amounts of heat from the tropics to the northern hemisphere, but fresh water is less dense than salt water. When you dump a huge amount of fresh water into the North Atlantic, it floats on top and prevents the normal sinking of cold, dense water. This can slow down or shut down the AMOC, and when the AMOC stops, the northern hemisphere stops receiving that massive heat transport from the tropics. Temperatures crash, and you're back to near glacial conditions. The Younger Dryas had effects far beyond the North Atlantic. Climate patterns shifted across the globe. Some regions got drier, others wetter, temperatures changed, and this had huge impacts on ecosystems and the animals living in them. For the great beasts that were already stressed by changing habitats, as the climate warmed and forests expanded, the Younger Dryas cold snap might have provided a temporary reprieve, but it also added instability to an already unstable situation. And it had major impacts on human societies, too. In the Middle East, this is right around the time agriculture first developed, some scientists think the climate stress of the Younger Dryas might have pushed hunter-gatherer groups to start deliberately cultivating plants as a way to end food security when wild resources became unreliable. If that's true, then this climate event, triggered by the 100,000-year cycle transitioning from glacial to interglacial, literally changed the course of human history, setting us on the path to farming, settled civilizations, and everything that followed. But eventually, around 11,700 years ago, the Younger Dryas ended, and it ended just as abruptly as it started. Temperatures spiked upward again. In some regions, temperatures rose by 10 degrees Celsius or more in just a decade or two. That's mind-bogglingly fast for natural climate change. The AMOC kicked back into gear. Heat flooded northward again. Ice sheets resumed their collapse, and this time there was no going back. The transition to full interglacial conditions was complete. We call this the beginning of the Holocene, our current geological epoch, and it marks the end of the last glacial period. For the megafauna, this was catastrophic. They had evolved over hundreds of thousands of years to thrive in cold, open grassland environments. But as the Holocene began, those environments were disappearing. The mammoth steppe, that unique ecosystem of cold grasslands that had supported enormous populations of large herbivores, was transforming. Forests were expanding. Grasslands were shrinking. The climate was getting wetter and warmer. For animals adapted to cold and dry conditions, this was a crisis, and the extinctions came fast. In North America, most of the megafauna disappeared between about 13,000 and 11,000 years ago. Mammoths, mastodons, horses, camels, giant ground sloths, saber-toothed cats, dire wolves, giant short-faced bears, all gone within a few thousand years. That's 70 to 80% of large mammal species just vanished. I find that truly staggering. I find myself returning to the sheer scale of loss during what we call the Quaternary Extinction event. It was utterly devastating. Europe, too, saw similar disappearances, though the exact timing shifted from species to species. Woolly mammoths vanished from most places, clinging on only in isolated pockets like Wrangler Island. Woolly rhinos disappeared entirely. Cave lions, giant deer, gone. The megafauna that had dominated Europe during the Ice Age were either gone or drastically reduced in number. South America suffered just as much. Giant ground sloths, all the different species that had evolved there, vanished. Glyptodons, native horses and camels, toxodons, macrochenia, giant armadillos, all gone. The extinction wave swept through the Americas like wildfire. Australia had already lost most of its megafauna earlier, between about 50,000 and 40,000 years ago. Giant wombats, enormous kangaroos, massive flightless birds, even a marsupial lion, all disappeared. The timing in Australia, though, seems to coincide more with the arrival of humans than with the last deglaciation, and this adds another layer to the puzzle. What truly caused these extinctions? This question has been debated for decades, and honestly, it's still not completely settled. There are two main schools of thought: the climate change hypothesis and the human hunting hypothesis. The truth, as is so often the case, is probably a combination of both, with the relative importance of each varying by region and species. The climate change hypothesis suggests that the rapid warming and the transformation of ecosystems were simply too much for these animals to handle. Megafauna had evolved for cold, open habitats. When those habitats disappeared in just a few thousand years, they couldn't adapt quickly enough. As forests expanded and grasslands shrank, megafauna populations became fragmented into smaller and smaller pockets of suitable habitat. Small, isolated populations are vulnerable to inbreeding, disease, and random environmental fluctuations. This creates a kind of extinction vortex, where declining populations face multiple threats that compound each other, and recovery becomes impossible. There's certainly good evidence for climate being a major factor. The extinctions happened during a period of incredibly rapid climate change. Species adapted to cold climates, like woolly mammoths and woolly rhinos, went extinct, while species adapted to forests or warmer climates generally survived. This pattern strongly suggests that climate played a significant role. Also, megafauna had survived previous deglaciations. The 100,000-year cycle means there were multiple transitions from glacial to interglacial conditions over the past few million years. If megafauna survived those, why not this one? That's where the human hunting hypothesis comes in. Modern humans had spread across most of the world by the end of the last ice age, And humans are incredibly effective hunters, especially with the technological innovations that developed during this period. Atlatls, which are spear throwers that dramatically extend range and power. Sophisticated hunting strategies involving coordinated groups, and later, bows and arrows. Human populations were growing and spreading into new territories. Critically, many megafauna had little or no evolutionary experience with human hunters when humans first arrived in the Americas or Australia. The local megafauna hadn't evolved fear responses to these two-legged predators. They were, in effect, naive prey. Modern examples illustrate this pattern clearly. When humans first reached oceanic islands with no previous human presence, the native birds and mammals often showed no fear and were easily hunted to extinction within decades or centuries. The same might have happened with Ice Age megafauna. They simply didn't recognize humans as threats until it was too late. And here's the thing about hunting megafauna. You don't need to hunt intensively to drive them extinct. These animals have slow reproductive rates. A female mammoth might have a calf only every 5 years, and mammoths don't reach sexual maturity until they're teens. If you kill even a few individuals per year from a population, especially females of reproductive age, you can drive the entire population into decline. Mathematical models show that even very low-intensity hunting, killing just a few percent of the population per year, can drive large-bodied animals extinct over centuries or millennia. And we know humans hunted megafauna. We found butchered mammoth bones at human sites, spear points embedded in mammoth ribs, kill sites where multiple animals were driven off cliffs or into traps and then butchered, even cave paintings showing hunting scenes. The evidence is undeniable that humans hunted these animals. The question, though, is whether hunting alone could cause extinctions, or whether it was just the final straw for populations already struggling with climate change. The timing is certainly suspicious in many regions. In North America, the extinctions coincide almost exactly with the expansion of Clovis culture, a group of humans with particularly effective hunting technology. Clovis points, these distinctive spear points, are found at sites with butchered mammoth remains. Within a few thousand years of Clovis people spreading across North America, the megafauna were gone. That's awfully coincidental timing. A study of the Anzac child, the only known Clovis individual, provides some interesting evidence. This was an 18-month-old child buried about 12,700 years ago in Montana. Scientists analyzed isotopes from the bones to reconstruct the diet of the child's mother. And they found that mammoth contributed around 40% of the maternal protein diet, similar to the diet of specialized mammoth predators like scimitar cats. This suggests Clovis people were heavily targeting mammoths, possibly as specialized mammoth hunters. But we need to be careful not to overinterpret. The Anzac child is one individual. We can't say all Clovis people had the same diet or hunting focus. The disappearance of the Ice Age giants. It wasn't a simple story. The debate continues about just how many humans there were, and whether such small populations could truly have hunted mammoths to extinction across an entire continent. Some scientists I know remain skeptical, and the extinction patterns themselves, they're not uniform. Some species vanished early, others lingered. The mammoths on Wrangel Island, for instance, survived until about 4,000 years ago. millennia after their mainland cousins disappeared. Cave bears went extinct even before many others. Dire wolves faded away, while gray wolves persisted. Bison, though heavily hunted, somehow endured. The reasons why some species survived while others didn't, well, it's still a puzzle we're piecing together. What's clear, though, is that the combination of climate change and human prey proved devastating. Climate change weakened megafauna populations by fragmenting their habitats and shrinking their food supply. Human hunting then prevented these already struggling populations from ever recovering. Together, these factors created a perfect storm, and there may have been other indirect consequences too. Humans extensively used fire to manage the land, which altered vegetation patterns. The loss of the megafauna themselves also disrupted the ecosystem. Mammoths and other large herbivores, you see, acted as ecosystem engineers, maintaining open grasslands. When they vanished, those grasslands gradually transformed into forests, further diminishing the habitat available for any remaining megafauna. It was a cascade of interconnected effects. The 100,000-year cycle had sustained these megafauna for hundreds of millennia. During the cold phases, they thrived. During the warm phases, they retreated to refuges. Then, with the return of the cold, they expanded again. It was a rhythm to which life had adapted. But this time, as the cycle shifted toward warming, a new factor emerged. Humans, armed with sophisticated hunting technology and ever-growing populations. The convergence of rapid climate change and human prey proved too much for most megafauna to bear. And within a few thousand years, that Ice Age world of giants was gone forever. But the story of the humans who lived through these 100,000-year cycles is equally fascinating. And when I say humans, I'm referring to multiple species. We weren't alone during the Ice Age. Neanderthals were already well established when our ancestors arrived, and they deserve far more recognition than they often receive. They were the original Ice Age survivors. They evolved in Europe and parts of Asia hundreds of thousands of years ago, enduring glacial cycles long before modern humans even left Africa. They weren't some brutish, primitive dead end. They were sophisticated, intelligent humans who had adapted remarkably well to glacial conditions. Their adaptations, brilliant, really. Consider their body structure. Neanderthals were short and stocky, with barrel chests and thick, heavy bones. The average male stood only about 160 centimeters tall, but they were built like tanks. Seriously muscular, with bones revealing massive muscle attachment sites. This wasn't random. It was an adaptation to the cold. Shorter, stockier bodies have less surface area relative to their volume, meaning less heat loss. It's Bergmann's rule in action, the same principle that led to the immense size of Ice Age megafauna. In cold climates, compact bodies retain heat more efficiently, and their faces were distinctive with large noses and wide nasal passages. This wasn't for mere appearance. Those large nasal cavities acted like built-in air conditioners, warming and humidifying the frigid, dry air before it reached the lungs. Breathing super cold air repeatedly can damage lung tissue, so this was crucial. It's the same adaptation we see in woolly mammoths with their enlarged sinuses. Different species, same solution to the same problem. Convergent evolution at work. But physical adaptations only tell part of the story. Neanderthals possessed sophisticated culture and technology. They crafted complex stone tools using the Levallois technique, carefully preparing a core and then striking off flakes of predetermined shapes. This required planning and mental visualization. You had to see the finished tool in your mind before you even started working the stone. They also fashioned wooden spears, carefully shaped and balanced, with tips hardened by fire. Some of these spears have been found preserved in German peat bogs, and they're beautifully crafted. Neanderthals hunted big, dangerous game. We've unearthed Neanderthal sites containing bones of bison, reindeer, wild horses, even woolly rhinoceros and mammoth. These weren't scavenged carcasses. The bones bear clear butchery marks made with stone tools while the meat was fresh. Neanderthals actively hunted animals that could easily kill them if the hunt went awry. That required coordination, communication, planning, and courage. They used fire extensively and effectively, not just for warmth and cooking, but also for creating complex adhesives. Archaeologists have discovered Neanderthal tools with birch bark tar used to attach stone points to wooden handles. Making birch bark tar requires heating birch bark in the absence of oxygen at specific temperatures. It's a multi-step process demanding technical knowledge and careful control. You couldn't just stumble upon figuring this out. They understood the process and could replicate it reliably. Even more impressively, Neanderthals possessed symbolic culture. They created ornamental objects, pierced shells, and eagle talons that were apparently worn as jewelry. They used pigments, possibly for body painting or decorating objects or cave walls. And they buried their dead, sometimes with what appear to be grave goods or in deliberate postures. There's the famous burial at Shanidar Cave in Iraq that includes evidence that might suggest flowers were placed in the grave, though that remains debated. But I think it's very interesting indeed. The question of why the Neanderthals disappeared has always haunted me. They were capable, well adapted, and yet, around 40,000 years ago, they vanished. Modern humans, having spread from Africa and the Middle East, were certainly present in Europe by then. The timing feels deliberate. Did we outcompete them, absorb them through interbreeding, or did we directly cause their extinction? The truth, as always, is complex. Genetic evidence shows that Neanderthals and modern humans did interbreed. If you have European or Asian ancestry, you likely carry 1 to 2% Neanderthal DNA. It might not seem like much, but it proves our ancestors had children with Neanderthals, and those children survived to have children of their own. Some Neanderthal genes persist today, influencing our immune function, skin and hair traits, and even our susceptibility to certain diseases. So, in a way, Neanderthals didn't completely disappear. They were absorbed into the modern human gene pool. However, as a distinct population with their own culture and identity, they did not survive. One major factor was likely demographics. Modern human populations seemed larger and more widespread. When two populations compete for resources, the larger one usually wins through sheer numbers. Even if individual Neanderthals were as capable as individual modern humans, being outnumbered 10 to 1 would eventually lead to their being overwhelmed. Modern humans also seem to possess technological advantages. While Neanderthals made excellent tools, we developed more diverse and specialized toolkits. We crafted fine bone needles for sewing fitted clothing, which provided better insulation than simply wrapping hides. We invented fishing equipment like hooks and harpoons, expanding our food sources. We created more elaborate art and ornaments, perhaps indicating more complex social structures or communication systems. Our trade networks were also wider. Materials found at modern human sites originated from hundreds of kilometers away, showing extensive exchange of goods. Neanderthal trade networks were more localized. Trade isn't just about resources, it's about information exchange and social connections. Wider networks mean more people sharing ideas and innovations, accelerating cultural evolution and adaptation. Some researchers believe modern humans may have had slightly better language abilities, enabling more complex planning and coordination. Or perhaps our social structures were more effective at resource acquisition or child rearing. These are subtle differences not easily visible in archaeological remains, but over generations they could compound into significant advantages. Climate, too, might have played a role. The late Ice Age was incredibly unstable, with rapid shifts between cold and warm periods. Perhaps Neanderthals, specialized for cold, stable conditions, struggled more with these fluctuations. Modern humans, coming from Africa with its own climate variability, might have been more adaptable. But this is speculative. We don't truly know. What's clear is that by 40,000 years ago, Neanderthals were gone, and modern humans were the only human species left in Europe. And we were spreading everywhere, adapting to every environment Earth offered. By the end of the last glacial period, humans had reached every continent except Antarctica, surviving the most extreme phase of the 100,000-year cycle. During the late Ice Age, modern humans developed an impressive array of technologies. Projectile weapons were a game changer. Early humans used thrusting spears, requiring close proximity to prey, dangerous when hunting mammoth. Then came the atlatl, a spear thrower that acted as a lever arm, dramatically increasing throwing range and power. Suddenly, attacks could be launched from tens of meters away, much safer. Later, probably between 20 and 30,000 years ago in some regions, humans invented the bow and arrow. This was huge. Arrows are faster and more accurate than atlatl darts. More ammunition could be carried. Hunting smaller, faster animals became more effective. The bow might be one of the most important technological innovations in human history, fundamentally changing how humans acquired food and defended themselves. Hunting strategies also became more sophisticated. There's evidence of drive hunting, where groups herded animals toward cliffs or into constructed traps. Sites with hundreds of bison or horses driven off cliffs and butchered reveal this. This requires serious coordination among large groups of people, scouts, drivers, people at the cliff to finish off injured animals, butchers, all working together with precise timing. It's complex social behavior requiring communication and planning. Fishing also became important. Humans developed harpoons, fish hooks made from bone, and nets, opening up aquatic resources as a vital part of our diet. Ice Age humans weren't just struggling to survive, they were creating. I find that fact incredibly moving. They had rich inner lives, spiritual beliefs, and cultural traditions. They were, in essence, fully modern people, even if the world they inhabited would feel incredibly harsh to us. Fishing became a major food source, especially in coastal and river areas. It was a relatively low-risk activity when compared to hunting mammoths. Coastal sites reveal that they intensively harvested fish and shellfish, leaving behind enormous shell heaps that represent thousands upon thousands of meals. Clothing technology improved dramatically as well. Around 40,000 years ago, bone needles appear in the archaeological record. These weren't just for any sewing. They were for creating fitted clothing with sleeves and clothes. If you've ever tried keeping warm by simply wrapping animal hides around yourself, you know how ineffective that can be. Fitted clothing is far better at trapping body heat. This technology likely allowed humans to survive in even colder regions and remain active during the winter, instead of simply hunkering down. Shelter evolved, too. In regions where wood was scarce, people built structures using mammoth bones and tusks as a framework, covering them with hides. These mammoth bone houses have been found in Ukraine and Russia. Some used bones from dozens of individual mammoths, representing thousands of kilograms of material. These were substantial dwellings, not temporary camps. People were investing serious effort into creating comfortable, long-term living spaces. And let's not forget the art. Ice Age humans created stunning artwork. Cave paintings like those at Lascaux and Chauvet in France are justly famous. These aren't crude drawings. They're sophisticated, dynamic images of animals rendered with incredible skill and accuracy. The artists used the natural contours of the cave walls to create three-dimensional effects. They mixed pigments to achieve different colors. They understood techniques like shading and perspective. Some paintings even show animals in motion, running or fighting, capturing movement in a static image. But it wasn't just cave paintings. People carved figurines from ivory, bone, and stone. The Venus figurines, stylized female forms found across Europe, date to this period. Some have elaborate details like hairstyles or clothing carved into them. People made musical instruments, flutes carved from bird bones or mammoth ivory. They created elaborate burials with grave goods, including thousands of ivory beads sewn onto clothing. One burial of children at Sunir in Russia included so many beads that researchers estimate it would have taken thousands of hours to make them. These people valued symbolic expression enough to invest enormous time and effort into it. Why did humans create art? Probably for many reasons. Some cave art might have been connected to hunting magic or spiritual rituals. Some figurines might have been religious or fertility symbols. Some art was probably just for aesthetic plea or social bonding. Human populations during the Ice Age weren't huge by modern standards. Estimates suggest maybe just a few million people worldwide, but those people had spread across most habitable regions. They'd reached Australia by at least 65,000 years ago, crossing significant water gaps even during low sea levels. They'd spread throughout Asia and Europe, and, critically, they'd made it to the Americas. The peopling of the Americas is fascinating. During peak glaciation, when sea levels were low, the Bering Land Bridge connected Asia and North America. But this wasn't just a narrow strip. Beringia was a vast region, probably thousands of kilometers wide, with its own ecosystems. Humans crossed it, likely following game animals, entering a continent with no previous human population and megafauna that had never encountered human hunters. The timing is still debated. The oldest widely accepted sites in the Americas date to about 15 to 16,000 years ago, but there are controversial sites that might be older, suggesting people could have arrived as early as 20 to 30,000 years ago. Either way, once humans were in the Americas, they spread incredibly fast. Within just a few thousand years, there's evidence of human presence from Alaska to the southern tip of South America. That's an incredible migration speed, and remember, the American megafauna went extinct shortly after humans arrived. Mammoths, mastodons, giant ground sloths, horses, camels, all gone within a few thousand years of human appearance. The timing suggests humans played a major role. The Clovis people, with their distinctive spear points and apparent focus on hunting mammoths, have been particularly implicated. But it's complicated. Climate was changing rapidly at the same time. It's probably both factors working together. By the time the Holocene began 11,700 years ago, humans were the dominant large animal on multiple continents. We'd outlasted Neanderthals and other human species. We'd survived the wild climate swings of deglaciation. We'd adapted to every environment from tropical rainforest to Arctic tundra. And we developed incredibly diverse cultures and technologies. Despite being one species genetically, humans showed cultural diversity that no other species has ever matched. This set the stage for what came next, the development of agriculture and the rise of civilization. But that's a different chapter in the story. The point is, the Ice Age and its 100,000-year cycle was the crucible that forged modern human behavior, the technological innovations, the social structures, the symbolic thinking, all developed or were refined during the harsh conditions of glacial cycles. We are, in a very real sense, products of the Ice Age. Our success as a species was built on adaptations to a frozen world, and now that world is gone, melted away as the cycle shifted to its warm phase. The question is, I sometimes wonder if we're truly adapted to the world we inhabit now, or if we're simply carrying baggage from an ice age that ended millennia ago. That 100,000-year cycle has shifted, you see. The ice has melted, the megafauna are mostly gone, and we humans now live in a world utterly different from what our ancestors knew for hundreds of thousands of years. Welcome to the Holocene, our current interglacial period, a time when everything began to change for human societies. Around 11,700 years ago, the Younger Dryas cold snap finally ended, and temperatures rose rapidly, stabilizing into conditions similar to today. The climate became warmer and wetter than it had been during the glacial period. Forests expanded massively, spreading across what had been cold grasslands and tundra. Sea levels continued to rise as the last major ice sheets melted, flooding coastlines and creating the geography we recognize today. The transformation was dramatic and relatively fast. For humans who'd been living as hunter-gatherers, this was both an opportunity and a challenge. On one hand, warmer temperatures meant longer growing seasons, more diverse vegetation, and a more predictable climate. But on the other hand, the megafauna they'd been hunting were disappearing. Those massive herds of mammoth, bison, and horses that had been reliable food sources were gone or going extinct. Humans had to adapt their subsistence strategies quickly or face serious problems. In some regions, people turned heavily to fishing and gathering shellfish. Coastal sites from this period show enormous shell middens and fish bone deposits. The ocean was stable and productive, providing reliable food. In other regions, people focused more on smaller game like deer, rabbits, and birds, supplemented with gathered nuts, seeds, roots, and berries. These required different hunting techniques than megafauna hunting. You can't drive deer off cliffs effectively. You need different tools, different strategies. But in a few special regions, something revolutionary happened. People started deliberately planting and cultivating wild plants. This was the beginning of agriculture, and it changed everything about human society. The first clear evidence of agriculture appears in the Fertile Crescent of the Middle East around 11 to 10,000 years ago. People started cultivating wheat and barley, domesticating sheep and goats. In China, rice and millet cultivation began around 9,000 years ago. In Mesoamerica, maize was domesticated around the same time in multiple regions independently, within just a few thousand years of each other. Humans invented farming. Why did agriculture develop when it did? That's been debated forever. One theory is population pres. During the Ice Age, human populations were kept relatively small by harsh conditions and limited food resources. But as the Holocene began and conditions improved, populations might have grown to the point where hunting and gathering couldn't support everyone. Agriculture produces more calories per unit of land than hunting and gathering, so it can support higher population densities. If your population outgrows your hunting territory, you either starve, migrate, or innovate. Some groups chose innovation. Another theory emphasizes climate stability. Agriculture requires planning for the future. You plant seeds and wait months for harvest. This only makes sense if you can reasonably predict that conditions will remain suitable for plant growth. During the wildly fluctuating climate of the late Ice Age, with events like the Younger Dryas, that wasn't a safe bet. But during the Holocene, climate became more stable and predictable. You could plant in spring and be reasonably confident summer would come and your crops would mature. This stability made agriculture viable in a way it hadn't been before. There's also a theory that the Younger Dryas specifically triggered agriculture in the Middle East. The idea is that hunter-gatherers in the Fertile Crescent had developed semi-sedentary lifestyles during the warm period before the Younger Dryas, living in villages and intensively harvesting wild grains. Then the Younger Dryas hit, and those wild grains became less productive. To maintain their lifestyles and avoid starvation, people started actively cultivating the grains, selecting for varieties that produced more food. When the Younger Dryas ended, they were already farming and just continued. Whatever triggered it, agriculture spread rapidly once it started, and it came with a massive package of changes to human society. You can't be nomadic and farm effectively. You need to stay in one place to tend crops and protect them from animals and thieves. So agriculture led to permanent settlements, villages that grew into towns and eventually cities. These settlements required new forms of social organization. Who controls the land? How do you store surplus food? How do you defend your settlement? How do you resolve disputes? Agriculture also changed human diets dramatically, and not always for the better. Hunter-gatherers typically had diverse diets with lots of protein and varied nutrients from many plant and animal sources. Early farmers ate mostly carbohydrates from a few grain crops, supplemented with whatever else they could grow or gather. Skeletons from early agricultural societies show signs of nutritional stress compared to hunter-gatherers: more cavities from all the starchy foods, shorter average stature, diseases associated with dietary deficiencies. Agriculture allowed population growth, but individual health often declined. Disease became a much bigger problem once humans started living in permanent settlements. When you're nomadic and moving frequently, your waste gets left behind and diseases don't have time to build up. But in permanent villages, the rise of agriculture wasn't just about growing food. It was about creating entirely new conditions for how we lived and even for what diseases could thrive. With higher population densities, waste accumulation, contaminated water, and close contact with domestic animals, early farming communities became breeding grounds for infectious diseases. It's sobering to realize that many of the diseases that plague us today, measles, smallpox, tuberculosis, influenza, originated in domestic animals, jumping to humans as we lived in closer quarters with livestock. Farming, in a way, made us more vulnerable, but it also offered an overwhelming advantage: the ability to support far more people per unit of land. A square kilometer of wheat fields could feed dozens, even hundreds of people, while the same area of wild land might support only a handful of hunter-gatherers. This meant agricultural societies could grow much larger. More people meant more workers, more soldiers, more inventors, more of everything. And when these agricultural societies encountered hunter-gatherer communities, the farmers usually prevailed through sheer numbers, even if the individual hunter-gatherers were healthier or better warriors. Over millennia, agriculture spread across most of the world where the climate allowed. Sometimes this happened through the migration of farming peoples, displacing or absorbing hunter-gatherers. Other times, hunter-gatherers adopted farming from their agricultural neighbors. Either way, most humans transitioned from a mobile hunting and gathering lifestyle to a sedentary farming existence. This set the stage for the rise of complex civilizations. Permanent settlements grew into cities. Cities required food from the surrounding agricultural areas, which led to the development of trade networks. Trade, in turn, required record-keeping, and that led to the invention of writing in multiple regions independently. Complex societies developed hierarchies with rulers, priests, craftspeople, farmers, and even slaves forming different social classes. Organized religion became more prominent, with monumental architecture like temples and pyramids built to honor gods or rulers. Specialized occupations emerged as some people focused full-time on pottery, metalworking, weaving, or administration instead of food production. The first civilizations emerged in river valleys where agriculture was particularly productive: Mesopotamia between the Tigris and Euphrates, Egypt along the Nile, the Indus Valley in South Asia, the Yellow River in China. These civilizations developed writing, mathematics, astronomy, metallurgy, all the hallmarks of complex society. And all of this happened within just a few thousand years after the end of the last ice age. The transformation from small, mobile hunter-gatherer bands to cities with tens of thousands of people is incredibly rapid on a geological scale. It's easy to fall into the trap of thinking this was a universal, inevitable change. But while these civilizations were rising, there were still hunter-gatherer societies thriving in other parts of the world. Australia's Aboriginal peoples, for instance, maintained their hunter-gatherer lifestyles for tens of thousands of years after agriculture was invented elsewhere. In the Americas, many groups remained hunter-gatherers, even while others developed agriculture and built cities. In Africa, groups like the San people hunted and gathered successfully until very recently, and some still do. Agriculture wasn't inevitable or universally adopted. It was one strategy among many, one that happened to be very successful at supporting large populations in complex societies, but not the only viable way to live. The ecological consequences of this transition were profound. It wasn't just about the extinction of megafauna. Forests expanded dramatically, changing countless ecosystems. Species adapted to open grasslands had to move, adapt, or go extinct. Cold-adapted species retreated northward or to higher elevations, while warm-adapted species expanded their ranges. The distribution of species across the planet shifted massively within just a few thousand years. And humans were increasingly shaping these ecosystems, often in ways we didn't fully appreciate until recently. Indigenous peoples around the world used fire as a landscape management tool, burning regularly to maintain open areas that attracted game animals or promoted the growth of useful plants. This burning had huge effects on vegetation patterns. What we often think of as natural, pristine ecosystems are actually anthropogenic, shaped by thousands of years of human fire management. In Australia, Aboriginal burning transformed large areas from dense forest to open woodland and grassland. In North America, Native American burning maintained vast prairies and savannas that might otherwise have been forested. When Europeans arrived and disrupted these burning practices, ecosystems often shifted dramatically. Forests grew in where they hadn't been for millennia. Fire-adapted species declined, while fire-sensitive species increased. The wilderness Europeans saw wasn't pristine nature. It was often the result of thousands of years of active human management. The extinction of megafauna also had cascading ecological effects that we're still working to fully understand. Megaherbivores like mammoths weren't just eating plants. They were ecosystem engineers. They knocked down trees, maintained open areas, distributed nutrients through their dung, and created trails and wallows. When they disappeared, these functions disappeared too. Some scientists believe that forests expanded after the Ice Age partly because there were no longer giant herbivores suppressing tree growth. There's even a hypothesis that megafauna extinction contributed to climate change. Large herbivores produce a lot of methane, a potent greenhouse gas, from their digestive systems. When megafauna populations crashed, methane emissions might have decreased significantly, and the transformation from open grasslands to forests changed the reflectivity of the land surface, affecting how much solar energy was absorbed versus reflected. The loss of those giant creatures, the megafauna, it wasn't just a loss of food for early humans. I think about the mammoth ivory used for tools, art, even construction, hides providing clothing and shelter, bones used for everything from needles to the very frames of dwellings. I imagine the disappearance of these animals forced humans to find substitutes, which likely spurred technological innovation. In a way, the extinction of the megafauna might have accelerated the transition to agriculture in some regions. If your primary food source vanishes and you can't find a suitable replacement through hunting smaller game, you either starve or find a new way to survive. Agriculture became that new way. The extinctions that ended the Ice Age world might have inadvertently pushed humans toward lifestyles that would ultimately create modern civilization. The Holocene, the epoch we're in now, has been unusually stable compared to the climate fluctuations of the Pleistocene. There have been variations, warm periods and cold periods, droughts and floods, but nothing like the dramatic swings of the Ice Age, with its rapid warming and cooling events. This stability, I believe, is what helped civilizations develop. It's difficult to build cities and plan agriculture when the climate might dramatically shift within a single generation. But the Holocene stability allowed humans to make long-term plans and investments, building irrigation systems and monumental architecture that took decades or even centuries to complete. Different parts of the world, of course, experienced the Holocene differently. The Sahara Desert, now a vast and empty wasteland, was actually green and wet during the early Holocene. From about 11,000 to 5,000 years ago, increased monsoon activity brought more rain to North Africa. Rivers flowed through what is now desert. Lakes filled valleys. Vegetation covered areas that are now bare sand. People lived throughout the region, herding cattle and developing agriculture. I've seen rock art from this period depicting hippos, giraffes, elephants, animals that now seem impossibly out of place. But then, around 5,000 years ago, the African monsoons weakened, and the Sahara dried out relatively quickly. Within just a few centuries, the Green Sahara became the desert we know today. This desertification forced populations to migrate, many moving to the Nile Valley, where water remained available. Some historians believe this migration and concentration along the Nile contributed to the development of ancient Egyptian civilization. Climate change driving human migration, driving civilization development, all interconnected. Similar stories played out elsewhere. The Middle East was relatively wet in the early Holocene, supporting agriculture and early civilizations. But droughts have repeatedly stressed or collapsed civilizations there. In Mesoamerica, droughts have been linked to the collapse of Maya civilization. In the American Southwest, extended droughts forced the abandonment of settlements like Mesa Verde. Climate variability during the Holocene has been a constant factor shaping human history, even though the swings were mild compared to the Ice Age. And here we are now, roughly 11,700 years into the current interglacial period. Based on past interglacials, we should eventually slide back into glacial conditions at some point. Different models give different predictions. Some suggest we have thousands of years before the next glaciation begins. Others think tens of thousands of years. The orbital cycles are complex, and their effects don't always line up predictably. But there's a massive wild card: human activity. It's now affecting global climate on a scale that might override the natural cycles entirely. We've increased atmospheric carbon dioxide from the natural interglacial level of about 280 parts per million to over 420 parts per million. That's a 50% increase in just a couple of centuries. The ice core records going back 800,000 years show nothing like this. We're in completely uncharted territory, and this brings us to the big question: what happens next? So, here's where things get really interesting and, honestly, a bit scary. We've spent this whole time discussing how the 100,000-year cycle has controlled Earth's climate for millions of years, creating ice ages and shaping the evolution of life, including humans. But now, for the first time in the history of this cycle, one species has the power to override it, and that species is us. Some scientists believe we've already delayed or canceled the next glaciation. The extra carbon dioxide we pumped into the atmosphere warming the planet, making it unlikely that northern hemisphere summers will be cool enough to allow ice sheet formation even when the orbital cycles shift toward glacial conditions. We might have prevented the next ice age from ever happening. Sounds good, right? Nobody wants kilometers of ice covering Canada and Scandinavia again. But the problem is, we're not just preventing the next ice age. We're warming the planet way beyond normal interglacial conditions. And we're doing it incredibly fast. Let's talk about what we've learned from studying ice age cycles and why it matters right now. First, and most importantly, the climate system has tipping points. It's not linear or gradual. You can push the system for a while and see only small changes, then suddenly cross a threshold and boom, rapid dramatic shifts happen. The Younger Dryas is the perfect example. Gradual warming, then catastrophic freshwater flooding, then abrupt climate reversal within decades. The system flipped states faster than human lifetimes. We're seeing similar threshold behavior today in multiple parts of the climate. Ice sheets don't simply melt in a predictable way. They can appear stable for incredibly long stretches. And then, almost without warning, the melting accelerates dramatically, especially when they reach a critical tipping point. Ocean circulation patterns like the Atlantic meridional overturning circulation can weaken gradually before potentially shutting down with surprising speed. Even permafrost, frozen for millennia, can abruptly thaw, unleashing greenhouse gases that further amplify the warming. These aren't gentle, linear changes. We're talking about systems where even a small push can trigger a massive reaction, and we're pushing multiple systems towards their breaking points all at once. Arctic sea ice is declining dramatically. Since the 1970s, the minimum extent in summer has plummeted by about 40%, based on satellite measurements. Some models even suggest we could see ice-free Arctic summers within decades. And it's all connected by feedback loops. Ice reflects sunlight, while ocean water absorbs it. So, less ice means more heat absorption, leading to even more warming, and then more ice loss. The Greenland ice sheet is losing mass at an accelerating rate. Recent measurements show a loss of around 250 billion tons per year. Greenland holds enough ice to raise global sea levels by about 7 meters if it were to melt completely. While a total melt is unlikely in the near future, even losing a fraction of that over the coming centuries would have a devastating impact on coastlines around the world. And once significant melting begins, these feedback effects make it incredibly difficult to stop. A darker rock, now exposed, absorbs more heat. Meltwater lubricates the base of the ice, causing it to flow faster, and warm ocean water creeps underneath, melting the ice from below. It's a cascade of positive feedbacks, each amplifying the initial change. The West Antarctic ice sheet is particularly vulnerable because much of it rests on bedrock below sea level. Warm ocean water is already making its way underneath, causing melting. Some scientists believe that major portions of the ice sheet are already committed to collapse over the coming centuries, even if we were to halt warming today. If that happens, we're looking at 3 to 5 meters of sea level rise. Coastlines would be reshaped on a global scale, and hundreds of millions of people would be displaced. The carbon cycle is also being disrupted in ways that mirror the Ice Age cycles, but in reverse and at a far more rapid pace. During the glacial periods, carbon dioxide levels dropped to around 180 to 200 parts per million. During interglacial periods, they rose to about 280 to 300 parts per million. This roughly 100 parts per million swing took tens of thousands of years, driven by natural ocean and vegetation processes, but we've increased carbon dioxide by over 140 parts per million in just over a century. We're replicating the natural cycle's entire range in a tiny fraction of the time, and we're blowing past natural interglacial levels, venturing into territory Earth hasn't seen for millions of years. The last time carbon dioxide levels were this high was probably during the Pleistocene Epoch, around 3 million years ago. Back then, temperatures were several degrees warmer than today. Sea levels were 15 to 25 meters higher, and the Arctic was forested instead of ice-covered. That's the trajectory we're on if we don't change course. The rate of change is just as important as the magnitude. Ecosystems can adapt to gradual changes over thousands of years. Species migrate, evolution selects for new traits, and ecological communities reassemble. But when change happens in decades or centuries, there's simply no time for gradual adaptation. Species either move fast enough or they face extinction. We're already seeing shifts in the ranges of thousands of species. Plants are flowering earlier, animals are moving toward the poles or up mountains, and ocean species are shifting to cooler waters. Some species are adapting successfully, while others are not. And we're likely headed for another extinction wave, perhaps not as dramatic as the Megafauna extinctions, but significant nonetheless. Current extinction rates are already elevated above background levels, and climate change is adding another major stressor on top of habitat loss and pollution. Here's something that keeps scientists up at night. During Ice Age cycles, carbon dioxide changes were a feedback, not a forcing. Orbital variations changed the sunlight distribution, which affected temperature. These temperature changes then affected ocean chemistry and vegetation, which in turn changed atmospheric carbon dioxide. Carbon dioxide then amplified the temperature changes. It was a feedback loop within the system, responding to external astronomical forcing. But what we're doing is different. We're directly forcing carbon dioxide changes by burning fossil fuels. This is direct forcing, not feedback. And all those natural feedbacks that amplified carbon dioxide changes during Ice Age cycles, they're still operating, amplifying the changes we're causing. We're pushing on a system with built-in amplifiers, and we don't fully understand all of them or where the thresholds lie. Permafrost is a huge wild card. There's around 1,500 billion tons of organic carbon stored in frozen Arctic soils. That's roughly twice as much carbon as currently in the atmosphere. As the Arctic warms, permafrost thaws, and microbes start decomposing that organic matter, releasing carbon dioxide and methane. It's a classic feedback loop. Warming causes thawing. Thawing releases greenhouse gases, and greenhouse gases cause more warming. How fast this happens is uncertain, but the potential for permafrost to become a major additional carbon source is very real and, frankly, quite scary. The ocean has absorbed about 90% of the extra heat trapped by greenhouse gases so far, which has slowed atmospheric warming, but at the cost of warming the ocean itself. Warm water holds less dissolved oxygen, and we're already seeing expanding dead zones where oxygen levels have dropped too low to support most life. Marine organisms are stressed by warming, acidification from dissolved carbon dioxide, and oxygen loss simultaneously. Coral reefs are being devastated by repeated bleaching events. These ecosystems, which support enormous biodiversity, are collapsing. The climate is complicated, often counterintuitive. I find myself thinking about that a lot. Global warming, paradoxically, could even cause regional cooling in some areas. It's a sobering thought. The Atlantic Meridional Overturning Circulation, or AMO, shows signs of weakening. The data is noisy, and it doesn't stretch back as far as I'd like, but multiple lines of evidence suggest it might be slowing. If it weakens significantly or even shuts down entirely, it could cause regional cooling in parts of Europe. This is what happened during the Younger Dryas. What do we do with this knowledge? Well, understanding the 100,000-year cycle teaches us that Earth's climate is sensitive to relatively small forcing changes. The orbital variations that trigger ice ages are, in reality, tiny changes in seasonal sunlight distribution. Yet, they're enough to tip the system from one state to another when combined with feedbacks. And now, we're applying forcing much larger and faster than those orbital variations. The response will be substantial. It's just a question of how substantial and on what time scale. We also learn that climate has momentum. Ice sheets take thousands of years to grow, but can collapse much faster. Once you start major melting, stopping it is difficult. Ocean circulation changes can be hard to reverse. Some changes we're causing are essentially irreversible on human timescales. Even if we stopped all emissions tomorrow, temperatures would remain elevated for centuries as the ocean and atmosphere slowly equilibrate. Sea level would continue rising for centuries or even millennia as ice sheets keep responding to warming already in the pipeline. It's uncomfortable to think about, I know. We've probably already committed to significant changes, even with aggressive emission reductions. Some warming, some sea level rise, some ecosystem disruption is, as they say, baked in. The question is how much more we add. Every bit of additional warming makes things worse. Every tenth of a degree matters when dealing with systems that have tipping points. The paleoclimate record teaches us that rapid climate change is really hard on societies. Climate changes at the end of the Ice Age contributed to megafauna extinctions and forced major changes in human subsistence. Droughts during the Holocene have toppled civilizations, and those were natural variations. Societies had no control over them. We're causing changes faster and potentially larger than those natural variations. With over 8 billion people to feed and house, many in areas vulnerable to climate change, the implications are staggering. Coastal cities face flooding from sea level rise. Agricultural regions face shifting rainfall and more extreme weather. Water resources are stressed by changing precipitation and glacial melt. Tropical regions could see temperatures exceeding human survivability thresholds for outdoor work during heat waves. Island nations could literally disappear. The humanitarian implications are enormous and unequally distributed. Those who contributed least to causing climate change are often the most vulnerable to its effects. But understanding the problem is the first step toward addressing it. We know more about climate now than ever. We can see changes happening in real time with satellites and monitoring. We can model future scenarios with increasing accuracy, and we have technologies available that could dramatically reduce emissions if deployed at scale. Solar and wind are now cost competitive with fossil fuels in many places. Electric vehicles are becoming mainstream. Energy storage is improving. Carbon capture is being developed, though not yet proven at the necessary scale. The challenge isn't really technological anymore. It's political, economic, and social. Getting 8 billion people to coordinate on emission reductions, equitably distributing costs and benefits, navigating competing interests. That's the hard part. Climate change is the ultimate tragedy of the commons. Individual actors benefit from burning fossil fuels, but everyone suffers the consequences. Solving it requires collective action at a scale humanity has never achieved. Some people feel despair. The problem seems too big, changes too slow, obstacles too numerous. I get that. But humans have navigated existential challenges before. We survived the Ice Age through adaptation and innovation. We transitioned from hunting megafauna to agriculture, fundamentally transforming our relationship with the planet. We've overcome diseases, expanded lifespans, created technologies that would seem like magic to our ancestors. We're not helpless. We're just facing a problem requiring unprecedented coordination. The 100,000-year cycle will eventually resume, assuming we don't permanently alter it. The orbital mechanics haven't changed. Naturally, Earth would eventually slide back into glacial conditions tens of thousands of years from now. But we're writing a new chapter, one where human activity is a major climate driver, not just a responder. We're affecting the planet on a scale comparable to the astronomical forces that controlled climate for millions of years. No species has ever had this influence. It's both inspiring and terrifying. I often imagine future geologists studying sediments millions of years from now. They'll see a clear marker. They'll see isotope ratios reflecting massive carbon combustion, extinction signatures, novel materials like plastics, and concrete in sediment. They'll recognize something unprecedented happened during this brief moment. Whether they'll also see evidence that we successfully navigated the crisis, that's still open. The answer depends on what we do in the coming decades. The cycle reminds us that climate is dynamic, sensitive to forcing, full of feedbacks and tipping points. It's not a stable, unchanging background. It's an active system responding to inputs. For millions of years, those inputs were natural. Now we're adding a new input, and the system is responding. We're living through a moment unlike any other in Earth's long history. For the first time, a single species, us, understands the global climate system while simultaneously altering it. The knowledge and the power we possess are unprecedented. What we choose to do with them now will determine the trajectory of our planet for thousands, even millions of years. The Ice Age cycles have shown us that life is remarkably resilient. Earth has endured dramatic climate shifts before, and life has always found a way to survive, adapt, and even thrive. Life even survived the asteroid that wiped out the dinosaurs. It will survive this era too. The real question is whether human civilization as we know it will thrive, or will we face disruptions on a massive scale, disruptions that could have been avoided with foresight and decisive action? I began this exploration by talking about the mystery of the 100,000-year cycle and how scientists patiently unraveled it. Now, that very same scientific community is sounding the alarm about anthropogenic climate change, using the same rigorous methods that revealed the secrets of the Ice Age cycles. If we trust the science that explained the past, shouldn't we also trust its predictions for the future? It's becoming increasingly clear that we're pushing the system hard. We will see significant responses, and the window for avoiding the worst outcomes is rapidly closing. The Ice Age taught our ancestors to be adaptable and innovative. That resilience is in our DNA. We can harness those very traits to navigate the challenge we've created, but it requires collective and immediate action. The climate system operates with momentum and time lags. Actions taken today won't fully manifest for decades, but inaction today commits us to changes that will unfold for centuries to come. Every year of delay only makes the eventual response more difficult and disruptive. So, where does that leave us? We're 11,700 years into an interglacial period that should eventually come to an end. We're armed with an understanding of how climate works, and we're actively changing it faster than natural processes typically do. The 100,000-year cycle that shaped human evolution is now being overridden by human activity. We've become a geological force. The only question is whether we wield that power wisely or recklessly. The answer will determine what kind of planet future generations inherit and whether they will view us as ancestors who rose to the challenge or as a cautionary tale of a species that understood the problem but failed to act. The clock is ticking. The cycle that sustained life for millions of years is still operating in the background, but for the first time, it might not matter because, for the first time, one of the species it created has the power to override it. What we do with that power in the next few decades will determine not just our future, but the future of countless other species sharing this planet with us. The Ice Age is over. The question is, what comes next? And unlike our ancestors, who just had to survive the cycle, we have the power to shape it. That's both an incredible responsibility and an incredible opportunity. Time to see what we do with it.